In section 4.5, we're going to look at exponential growth and decay, and we're going to look at modeling data. First, we're going to look at the exponential growth and decay model. Next, we'll use the logistic growth model. Then we'll choose an appropriate model for a set of data. And lastly, we'll express an exponential model in base E. So this is a model whose base is not the number E, but we can rewrite it using base E. Our exponential growth and decay models. The mathematical model for exponential growth or decay is given by f of t equals a sub 0 e to the kt, or a equals a sub 0 e to the kt. So instead of using f of t, we use the variable capital A to represent the amount. If k is greater than 0, so it is a positive number, the function models the amount or size of a growing entity. A sub 0 is the original amount or size of the growing entity at time t equals 0. So A sub 0 is the amount of this quantity that you begin with. A is the amount of time t, and k is the constant representing the growth rate. Exponential growth can be represented by the graph you see down at the bottom on the left, where the quantity starts out rather slowly and then increases rapidly. If k is less than 0, or it's a negative number, the function models the amount or size of a decaying entity. A sub 0 is the original amount, or the size of the decaying entity at time t equals 0. So again, it's the amount of something you start with. A is the amount at time t, and k is the constant representing the decay rate. So exponential decay is represented by the graph on the right. It's decaying at a rapid rate, and then it starts slowing down as time increases. Let's look at an example. All right. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Now let's pause a second. Since the population over the years from 2000 to 2011, over those 11 years, increased from 807 to 1,052, this will be exponential growth. Use the exponential growth model, A equals A sub 0 e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So we are given everything that we need in this problem except the growth rate. We are not given k. We know the initial population is 807 million. So let's write that down. The initial population, the initial amount of stuff that I begin with is 807 million. So A sub 0 equals 807. And by the year 2011, it had grown to 1,052 million. So the population I have after 11 years is 1,052 million. So that's A. And they tell me this occurs from the year 2000 to the year 2011. So that's 11 years. So time is 11. T equals 11. So what we don't know is k. But I can substitute a sub 0, a, and t into my exponential growth model, and I can determine the growth constant, k. So let's do that. So we have 1052a equals a sub 0, 807, e to the k, I don't know, times t, which is 11. Now we have an exponential equation we can solve. To solve an exponential equation, you're going to isolate the exponential on one side of the equation. So on the right-hand side of this equation, I need to get rid of the 807. And I can do that by dividing both sides by 807. On the right-hand side of the equation, the 807 cancels, and I'm left with e to the 11k. Just going to use the commutative property of multiplication to rewrite that. And on the left-hand side, I'm going to leave this as that division. I'm not going to go ahead and divide that out and get a decimal approximation yet. So I'm going to leave that as 1052 over 807. Now, to solve this exponential equation, since the base is e, I need to take the natural log of both sides of this equation. So I'm going to take the natural log of the left and the natural log of the right. And when I take the natural log of the base e raised to a power, that's going to be just the power itself. The natural log of e to the 11k is equal to 11k. And on the left-hand side, I still have the natural log of 1052 divided by 807. All right, now to find k, I need to divide both sides by the number 11. So I'm going to take the natural log of 1052 divided by 807, and I'm going to divide that by 11, and that's going to give me k. So now it's time for me to take my calculator out and to determine a decimal approximation for this value. So I take my calculator out, I take the natural log of the quotient 1052 divided by 807. Then I'm going to take that value, whatever it is, and I'm going to divide it by 11. And when I do that, I get k is 0.024. And you'll probably want to carry that out to at least 3 decimal places. And note that k is a positive number, which is what I expected. I expected it to be positive because this is growth. The population is increasing, so this is exponential growth. So now I can write my model. A sub 0, the population that we began with, is 807 million. E, and we found k to be 0.024 times t. So there is our exponential model that models the growth in population in Africa. So on this slide, I'm asked, by what year will Africa's population reach 2,000 million or 2 billion? Again, when we found this model, A and A sub 0 was in millions. So we're going to want to substitute into this model A equals 2,000 and solve for T because we're interested in what year the population is 2,000 million. So we're going to solve now for T. So we're going to replace or substitute 2000 in 4a. And again, we're solving an exponential equation. We're solving this exponential equation for the variable t for time. So to solve an exponential equation, I have to isolate the exponential on one side of the equation. So again, I'm going to divide both sides by 807. And I'm going to leave that exact on the left-hand side of the equation until I'm done. So I have 2,000 over 807. The 807s cancel on the right-hand side of this equation, equals e to the 0.024 times t. So again, to solve an exponential equation whose base is e, I'm going to take the natural log of both sides. And when I take the natural log of e raised to a power, that's going to be equivalent to that exponent. And on the left-hand side, I still have that natural log. Now, to solve for t, I'm going to divide both sides by 0.024. All right, so now I get my calculator out and I take the natural log of 2,000 divided by 807. I get that amount, and then I take that and divide that value by 0.024. And I get t is approximately, because I am finding a decimal approximation, and I'm going to round this off to the nearest year. I get 38 years. So 38 years from the year 2000, because t represents the number of years since 2000. If I'm 38 years from the year 2000, I'm in the year 2038. So my answer is 2038. All right, the next example we're going to look at is exponential decay. The half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. Find the exponential decay model for strontium-90. So again, we're given everything we need to find the model except K. So we're going to find the decay constant K first, then we'll have a model we can use for anything else. All right, so what's it mean that the half-life is 28 years? So if I start, so at time t equals 0, if I start with an amount of this stuff, a sub 0, this means after 28 years, I now have half of what I began with. So A, the amount that I have after 28 years, is half the amount that I began with. And you could certainly write this as 0.5 a sub 0. So after 28 years, I only have half of what I began with. So now we're going to make all these substitutions and we're going to determine K. So my model is A equals A sub 0, e to the kt. A is 1/2 A sub 0 equals A sub 0. And it doesn't matter that I don't know exactly how many grams of this stuff that I begin with, because the A sub 0s are going to cancel out. E to the k times 28. And again, if I divide both sides by a sub 0, which I need to do to solve an exponential equation, I need to isolate the exponent by itself. When I divide both sides by a sub 0, they cancel out on both the right-hand side and the left-hand side. So I'm left with 1/2 equals e to the 28k. And now I'm going to take the natural log of both sides. And when I take the natural log of e to the 28k, I get 28k, natural log of 1/2, and then I divide both sides by 28. And so I'm going to take my calculator out, and I'm going to find the natural log of 1/2, and I'm going to divide that by the number 28, and I get k is approximately negative 0.0248. And I'm not surprised that this is a negative number. It should be negative because we're talking about exponential decay. As time goes on, the amount of this material, strontium-90, is decreasing. So this is exponential decay. So now I have my model. Here's my model right here. A equals a sub 0 e to the minus 0.0248 t. So now I can determine the time it takes for an amount to decay, or if I had the amount that I begin with and I know the half-life of this thing, I could figure out how much I have left over a certain time period. So it says, if there are originally 60 grams, how long will it take for strontium-90 to decay to a level of 10 grams? So I'm starting with 60 grams. So a sub 0 is 60. The amount I have after some time period is going to be 10 grams. So what I'm looking for is the time required for this to happen. So I'm going to make those substitutions and I'm going to solve for t. So I have 10 equals 60 e to the negative 0.0248 t, and I'm solving for t. To solve an exponential equation, I have to isolate the exponential on one side of the equation. So I need to divide both sides of the equation by 60. And I might note that I can cancel a 10 over on the left-hand side. 10 over 60 is the same as 1/6. Now you certainly don't have to cancel that. You could leave it as 10 over 60 until you take the logarithm, but I'm just going to save myself a little writing. The 60s cancel on the right-hand side. All right, so now I'm going to take the natural log of both sides. And when I take the natural log of e to the minus 0.0248 t, I get negative 0.0248 t, and that's equal to the natural log of 1/6. And I'm going to divide both sides by negative 0.0248. So again, I find my calculator and I take the natural log of the quotient 1 divided by 6, get that value, whatever that value is, and take that value and divide it by negative 0.0248. When you find the value for t, it should be a positive number. Doesn't make sense for time to go backwards. So t is approximately, and I'm going to round this off to the nearest year, I get 72 years. So it takes approximately 72 years for this element strontium-90 to go from original amount of 60 grams to an amount of 10 grams. All right, the logistic growth model. The mathematical model for limited logistic growth is given by f of t equals c divided by 1 plus a times e to the minus bt, or instead of writing f of t, we can write a, the amount we have after time t. A is c divided by 1 plus a times e to the minus bt. A, b, and c are all constants. C has to be greater than 0, as does b. So what do we mean by a logistic growth model or a limited logistic growth model? This is a model that represents growth that has a limit. So if it starts off increasing very rapidly, and then it starts slowing down, so it's increasing very rapidly down here, but at this point here, the increase in growth starts slowing down until it reaches this plateau. So it actually approaches a horizontal asymptote. This is logistic growth. And this happens quite often in nature. If, for example, you put fruit flies in a jar with a certain amount of food, their growth rate is going to be initially exponential. They're going to go crazy. But if you don't replenish the food supply, eventually the growth rate is going to limit. That's logistic growth rate. Let's look at an example. In a learning theory project, psychologists discovered that f of t equals 0.8 divided by 1 plus e to the minus 0.2t is a model for describing the proportion of correct responses after t learning trials. Find the proportion of correct responses prior to learning trials taking place. So what they want you to find is t of 0. Before any learning trials take place, what is the proportion of correct responses? So we need to find f of 0. So I replaced t in my equation with the number 0. Negative 0.2 times 0 is 0. So we're raising e to the 0 power. However, whenever we raise a non-zero number to the 0 power, we get the number 1. So this is 0.8 divided by 2, or f of 0 is 0.4. So the proportion of correct responses before any learning trials take place is 0.4, or you could think of that as a percentage, 40%. All right. What happens after 10 learning trials? What is the proportion of correct responses? So now you're finding f of 10. So again, we're just going to replace t in our logistic model with the number 10. So this is something you're going to have to do on your calculator for sure. I might go ahead and determine what 0.2 times 10 is. And I'm going to get what? Negative 2. Negative 0.2 times 10 is negative 2. So now I'm going to take my calculator out and I'm going to do this calculation. Whether you use the fraction button on your calculator or use parentheses, however you want to do this. I would probably use parentheses. I'd say 0.8 divided by, and then I'm going to put that entire denominator inside parentheses, 1 plus, find my e to the x button, raise that to the negative 2, close my parentheses, and then hit enter. So when I do that, I should divide 0.8 by 1 plus e to the minus 2. And when I do that, I get f of 10, where's that at? I get approximately 0.7. Probably should use the squiggly equal there because it's approximate value. So after 10 learning trials, the proportion of correct responses is 0.7, or if you want to think of that as a percentage, 70%. All right, the last part of the logistic model example asks, what is the limiting size of f of t? The proportion of correct responses if continued learning trials take place. Since this is a logistic model, it is going to limit out. It's going to reach a horizontal asymptote and the graph becomes flat. And to find the limiting size of your logistic model, it's just the numerator. So that number right there is always the limiting size in your logistic model. So our limiting size is 0.8 or 80%. So the numerator of a logistic model is the limiting size. All right, modeling data. We have now looked at a lot of different types of functions. We've looked at linear functions, we've looked at quadratic functions, we looked at polynomial functions, we've looked at exponential functions, and logarithmic functions. So if you were to model data, chances are, not always, but chances are one of these functions could model your data. The first two models we have here, we've drawn scatter plots. And what's a scatter plot? A scatter plot is just when you plot your ordered pairs on a coordinate plane. So the first scatter plot we have there is exponential growth, just like what we just looked at just a few minutes ago. The second graph, the one in the middle there, when the points were graphed, it looks like exponential decay. In exponential growth, we start off kind of slow and then the growth takes off. In exponential decay, it's decreasing rapidly and then it slows down. The third model on this page is logarithmic. Logarithmic models, you're going to have a limit on your domain. Remember, logarithms, you can't take the logarithm of 0 or a negative number. You can only take the logarithm of a positive number. So when you get this kind of shape that we have in this third graph, where it looks like the domain is being limited, and then you have that increase, that's most likely logarithmic. So the model is y equals a plus b times the natural log of x. That is the logarithmic model. A has to be greater than 0, as does b in this type of model. Now we could also have a logarithmic model. And my slides are not catching up with me. I have to unshare and reshare here. Don't you love listening to me mumble? Let me try unsharing my screen and resharing it. There we go. All right, so on the previous slide, we had the logarithmic model, y equals a plus b natural log x. In that model, that shape represents the model where a and b are both positive. If you have a model where a is positive but b is negative, you get the shape that you see in the first graph there. So that would be a logarithmic model also. The last two graphs are linear models, where when we plot the data points on a coordinate plane, the scatter plot looks fairly linear. You have a linear equation that's increasing where the slope of that line is positive, and you have a linear model where the slope is negative. That's the last graph on the slide. All right, let's look at an example. Table 4.7 shows the population of various cities in thousands and the average walking speed in feet per second of a person living in the city. So if you have a city whose population is 5.5 thousand, average walking speed of the people living in that city is 0.6 feet per second. And you'll note that as the population increases, so does the walking speed. And that kind of human behavior-wise makes sense. So we take those 5 ordered pairs and we graph them on the coordinate plane. That gives us the scatter plot. And you can see the scatter plot in the graph on the right. And if I look at that shape of that set of ordered pairs, that looks very logarithmic to me. So I think that the model that would fit this data best is a logarithmic model. Now, it's beyond the scope of this course to determine what that model is, but you could do that. You could put this data in either Excel or your TI-83 or 84 calculator, and you could actually determine the model that fits this data the best. All right, our last topic, expressing y equals a times b to a power x in base e. If I have an exponential function, y equals a times b to the x, I can rewrite that in terms of base e, and that might not be a bad thing to do sometimes. The way we do that is we write it as y equals a times e to the natural log of b times x. So do you see what we did there? We replaced the base b with e, and then in the exponent of b, we place the natural log of that original base times our variable. So it's quite easy to do. So let's do an example. Rewrite y equals 4 times 7.8 to the x in terms of base e. First, express it in terms of a natural logarithm, and then round to 3 decimal places. So to write y equals 4 times 7.8 to the x, we rewrite that as 4 times e raised to the natural log of our original base, the natural log of 7.8 times x. So 4 times e to the natural log of 2.8 times x is equivalent to y equals 4 times 7.8 to the x. And I might, especially not to confuse my math lab, might put that natural log in parentheses. So my math lab knows what I'm talking about. We want to make sure that we know that we're multiplying the entire log of 2.8 times x. All right, so now I can find a decimal approximation to the logarithm of 2.8. And my calculator says that's approximately 2.054 to 3 decimal places. 2.054. So the natural log of 2.8 is approximately 2.054, and this is 3 decimal places. I've got the first decimal, the tenths place, the second, the 5 is in the hundredths place, and the 4 is in the thousandths place. So I have 3 decimal places. And that concludes section 4.4 on exponential growth and decay, the logistic model, and modeling data.